This video we're going to talk about complex conjugation, or the complex conjugate, which arises a lot of the time, and we need to make sure we know this and are comfortable with it. So if you've got a complex number, so if z is, say, let's call it x plus yi, where x is, as we've looked at, this is the real part, and y is the imaginary part, then the complex conjugate we denote as z star. So if we see that star, that's our notation for the conjugate, and with the complex conjugate we reverse the sign of the imaginary part of the complex number. So for example, if you had z was 4 plus 3i, then z star would just be 4 minus 3i. So notice it's the imaginary part that's changed sign, the real part stays the same sign. Okay, if you had z is minus 2 minus I, z star will be minus 2 plus I. Okay, that's all the complex conjugate is. And I mentioned in an earlier video about maybe spotting a pattern, and what you'll spot is that when we're looking at roots of complex equations, the roots, if they're not real, they occur in complex pairs, complex conjugate pairs. So one root is this, the other root is this, if we have real coefficients of the quadratic. So if a, b, c are real, they're in the real numbers, then that means the roots of this equation, if they are complex, will always occur in complex conjugate pairs. So this will be one root, say z1, and this would be the other root, z2, depending on the equation. But we'll see that happen as we go through this. So let's have a look. So let's look at our examples. We've got number 1. If z is 2 minus 7i, we've basically done this just now already, but just so you've got it formally written down. So z star will then be 2 plus 7i. So you just change the sign of the imaginary part. Find the value of z plus z star. Well, this is just 2 minus 7i plus 2 plus 7i. The imaginary parts will cancel. 2 plus 2 is 4. And the value of z star, is 1 multiplied by the other. 2 times 2 is 4. 2 times 7i is 14i. Minus 7i times 2 is minus 14i, so they will also cancel. And we're going to get minus 7i times 7i, and again, sorry, we should be thinking, well, hopefully getting a bit better at this. Minus 7 times minus 7 is 49. I times I is I squared, so it's 49 times minus 1. So this will just be minus 49. So the answer here will be 4 minus 49, which is minus 45. Sorry, I've just realised it wasn't minus 7i squared, was it? Minus 7i times 7i. So we'll actually get minus 7 times 7 is minus 49. I times I is I squared, so we'll actually get positive 49 here, won't we? Sorry, it's me making up a different question again. So we'll get 53 as my answer for this here. Okay, minus 7 times 7, minus 49. I times I squared, so it's minus 49 times minus 1 plus 49. Okay, but hopefully we can start skipping straight to this. That's question 1. Question 2. So write 5 plus 4i over 2 minus 3i in the form a plus bi. So we want to write this as a single complex number rather than one complex number divided by another complex number. So the way that this works is very similar to rationalizing the denominator when we're simplifying surds. So in order to rationalize the denominator here, although we're not rationalizing it, to simplify these kind of questions, we times the top and bottom by the complex conjugate of the bottom. So if we reverse the sign of the bottom complex number, so 2 minus 3i becomes 2 plus 3i, and we times top and bottom by 2 plus 3i. So we're still timesing by 1, we're not changing the value, but this is going to change what it looks like. So on the top we're going to get 5 times 2, 5 times 3i, 4i times 2, and 4i times 3i, 4 3s are 12, so this is 12i squared which is minus 12. Remember, I squared is minus 1. On the bottom, 2 2s are 4. We're going to get 2 times 3i is plus 6i. Minus 3i times 2 is minus 6i. So you'll notice, in similar to the surds, we get these imaginary bits to cancel out. With surds, you get the roots to cancel out, and the irrational parts. Here you get the imaginary parts to cancel out. And then minus 3 times 3, minus 3i times 3, you get minus 9i squared, so plus 9. And simplify, so we're going to get 10 minus 12 minus 2. 15 plus 8 is 23. 1 over 4 plus 9, which is 13. And then if we want to write it in the form a plus bi, we can just split this as minus 2 over 13 plus 23 over 13. They won't simplify I. And then we've got it as one complex number. So a is minus 2 over 13 and b is 23 over 13. Let's have a look at the next one. So number 3. Here we have w equals 4 over 8 minus I root 2. We could write root 2i, it doesn't matter which way around I write it. Express this in the form a plus bi root 2, where a and b are rational numbers. So again, we want to always write these complex numbers. We want to times top and bottom by the complex conjugate of the bottom, and that simplifies for us. So here we're going to have, I'm just going to write the root 2 in front. So I'm going to times by 8 plus root 2i over 8 plus root 2i. So I'll just change that sign of the conjugate on the bottom to get the conjugate, and then multiplied by it. So I get 4 8s are 32. Excuse me, 4 times root 2i is just 4 root 2i, all over 8 8s are 64. We know we're going to get something to cancel here, but let's just do it anyway. So we're going to get 8 root 2i and minus 8 root 2i. And I'm going to get minus root 2i times root 2i on the bottom, aren't I? So I'll get minus root 2 times root 2 is minus 2, and I'll get I squared. So it'll be minus 2 times minus 1, so this will be plus 2. Again, the more you practice that, the quicker and more confident you'll get with it. So we can simplify the bottom because these cancel. So we get 64, 65, 66. And then everything's even here, isn't it? So 2 will certainly divide everything. So if we do 2 into 32, we're going to get 16. We're going to get 2 root 2. And 2 into this goes 33. So 2 is common, so divide everything by 2. And then to get it in the form they want, 16 over 33 plus 2 root 2 over 33. I remember, always pay close attention to the question. It says a and b are rational numbers, so I'm quite happy with the fractions here. Yes, it's a little bit ugly because it's got these this root in it as well, but as long as we've done everything correctly, the correct method, then it should be fine. And the last one on this complex conjugate section is number 4. Complex number is defined by z equals p plus 5i over p minus 2i. P is a real number and P is positive. They tell us that. Given that the real part of Z, so the real part of Z, which we can write this, we can write the imaginary part of Z like this. So real part of Z is a half. Find the value of P. Okay, so if the real part of Z is a half, first of all we need to find what Z is. We need to split it into its real part. Like the question above, we've got a real part and we've got an imaginary part. So we want to kind of get it in that form, and then we can put the real part equal to a half because we're told that that's equal to a half in the question. So let's take Z. Whenever you see it in this form, chances are you'll be times in top and bottom by the conjugate. That's just pretty much always the way forward. On the top, P times P, P times 2i, 5i times P, and 5i times 2i is 10i squared, so minus 10. And on the bottom we get P times P, we're going to get plus 2pi minus 2pi, again they'll cancel. And we get minus 2i times 2i, which is minus 4i squared, so plus 4. So we end up on the top with p squared minus 10 as the real bit, and then 7p I, there's our imaginary bit, and then p squared plus 4 on the bottom. Okay, so still not particularly pretty, but there's my real bit over the denominator, and there's my imaginary bit over the denominator. Remember, I can always split it over the denominator like that. Separate the numerators out. Oops, sorry, it should be a plus. Okay, so then I've got my real part here, and I've got my imaginary part in front of the I here. So if I'm told the real part of z is a half, then I can just equate that real bit. So the real part, z equals a half. Therefore, this bit, the real bit, is equal to a half. Solve this, so times up by p squared plus 4. I'm going to times by 2 to get rid of the half. Times this side by 2, times this side by 2 will cancel the half. And we're going to minus p squared and add 20. So we get p plus or minus root 24, and we know that p is greater than 0. So therefore p must be the positive square root of 24, and this is root 4 root 6. So p is 2 root 6. And then the last little bit, I think I've run out of room here. Oh no, I'm okay. The last little bit says write z in the form a plus bi. So we know that z, this is part b, so z is, from our part a, we know the real part of z is a half, so I can put that in, and it says the imaginary part we worked out here, so it's going to be plus 7pi over p squared plus 4. So we just now need to put our value for p in here, and we get our full value for z. So this is a half plus, so we can get 7 times p over p squared plus 4, and just put the I afterwards. So we'll have a half, that's just going to tag along. So you get 14 root 6 on the top. 2 root 6 squared is 2 squared and root 6 squared. So we get 2 squared is 4 times by root 6 squared, which is 6, so 4 6 is 24. And then simplify. 7 is common. So 7 will cancel to give us 2 root 6. In fact, 14 is common, isn't it, obviously? So we get root 6 over 2. And that's fully simplified. And there's our z in the form a plus bi. So a is a half. And b is root 6 over 2. It's a very useful video. You've got your complex conjugates there, what they are, and how they work, and also this whole idea of kind of rationalizing the denominator. You're not rationalizing it, but it's the same kind of idea when you're trying to simplify a complex number which has a complex number on the denominator.